So we are playing around with chapter 6, section 6.1. Sinusoidal functions. AKA also known as wave functions. So these wave functions that we're graphing now, once we pull it off of the unit circle, they are how waves in the water work. They are how sound waves work. Radio waves, anything like that is related to these kinds of functions we're playing with. So a couple of functions we've messed around with so far is the sine, y equals the sine of x, and y equals the cosine of x. And what we're going to look at next is transformations of functions. So for example, if we take a function that we had, f of x, in this case, let's take f of x as the sine of x, and then we modify it by saying, what happens if I make a new function, y equals 2 times f of x? What does this new function look like? How is it different from the original? So in this case, f of x is the sine, so I want to know, what does twice the sine of x look like? So one way to think about this one right here is f of x here, it is the y value, and I've just doubled the y values. Now, I didn't do anything in here with x, so the x's should stay just like they were, but the y's should all double. So originally, that's 2 pi there, pi is right in the middle. My sine function went up and down and down and up, and it peaked at 1 and it bottomed out at -1. My prediction here, based on my previous experience in math, is that when I double the sine, that should double the y values, and I should get a peak up here. It's -2, that's +2, and I should get a peak down here. So doubling 1 gives me 2. If I double, say, like 1/2, there was a y value of 1/2, double that should be 1. If you double 0, you still get 0. So I think my function is going to look something like this. It's just going to be a taller wave. Let's look at a graphing calculator and see what we got. We'll do that in a couple of different ways. So I'm playing around with f here, so I'm going to turn off g, the cosine, and I made a new function by taking y equals 2 times f of x. And so there I can see I get this new green wave. Twice the sine wave is twice as tall. If I were to do something like add something outside of that, so if I make it another version of that function, like suppose, let's go blue, I looked at y equals f of x plus 1. Well, f of x is a y value. So I'm just adding 1 to all the y values. So that should take every point on the red curve, right? This point, this point, this point, this point, this point, this point, and it's going to move them up 1. Is what that should do right there. Let's check it out. So graphing calculator is going to be indispensable for this chapter. It's way easier than plotting things by hand. So let's get rid of that one. Take the original f of x. And so at first, I just said y equals f of x. It's sitting right on top of the sine. But then I'm going to add 1 outside, and that should take, again, every point on the red function and shift it up 1. So these function transformations are, the big ones are stretches, although we can compress, and shifts. right? So stretches and compressions and shifts. And so we just got to get back into the state of mind as to what we see algebraically versus what we see graphically. So summarize some you should be familiar with here. Function transformations. If you start with some function, y equals f of x, and then you transform with a multiple like a times f of x, since we're multiplying on the outside, that's affecting the y values. That means this is a vertical transformation, not a horizontal transformation. And it depends on the value of a. So earlier I put in 2 there. So I got a vertical stretch. Oops. When a, not x, when a was greater than 1. If I multiply by 1, nothing happens, right? 1 times something is itself. If I wanted to get a compression, then I would have to multiply by a fraction. So a fraction would be less than 1. And the problem with just thinking about greater than or less than 1 is that leaves out the idea of a negative, which we'll look at in a second. So to deal with that weird stuff that happens with a negative, what we do is we actually look at the absolute value of that multiple there. So if the absolute value of a is 1, we're going to get a vertical stretch. We're going to get a vertical compression when the absolute value of a is less than 1. Now, remember dealing with absolute values. If you want to get rid of the absolute value, you have to deal with a plus or a minus. And if you deal with plus and minuses with inequalities, then you have to flip an inequality. So if I wanted to rewrite, say, this one down here without an absolute value, it would look like this. It would say a is less than 1 and a is greater than -1. Think about that in a number line for a second. Here's 1 over there, -1 lives over there. So here I'm saying I'm looking for numbers that are less than 1. So less than 1 would be I could be 1, or I could be any number out that way. This one right here says a has to be, oops, I made a mistake there. That should not be a closed circle, it should be open. Because I can't actually be 1. And then for -1, this says you can be bigger than -1. So starting at -1 but not -1, you go this way forever. And the and means where do they overlap? So they overlap right in between here. So that means if absolute value of a is less than 1, that means a has to be between -1 and 1. So yet another way to write that inequality is a has to be less than 1 and greater than -1. So I can put it as a compound inequality like that. So let's check that out on the graphing calculator. All right, so I'm going to sneak in front of my y equals f of x here. I'm going to pick a number less than 1, like 1/2. And I can see my green wave is shorter, right? It's not as high, it's not as low, it's vertically compressed, right? So we ran this through some kind of squeezer that knocks it down. What if I did a -1.5? My claim is that's also going to be a squished wave. It's not going to be as tall as the original one. So I'm going to sneak a little negative in front there, and I can see, yep, it's squished also. Now the negative has an extra thing that happens. If you multiply a number by a negative, that changes positives here to negatives. It changes negatives here to positives. So that's another case we've got in terms of transformations. And again, this should be a review of your, hopefully your last math course. So we have if A in absolute value is greater than 1, so that would be, that breaks into two cases. A is greater than 1 or A is less than -1. If we plug in exactly 1, nothing happens. But if A is -1, then we get a vertical flip around the x-axis. So we get a vertical flip about the x-axis when A is negative, so less than 0. Could be -1, could be -0.5. Either way, what was once positive becomes negative, which was once negative becomes positive. So we get that vertical flip. The flip is about the x-axis. So that's vertical stretch, vertical compression, vertical flip all depend on that number A multiple on the outside of the function. So the other thing we looked at a few minutes ago, oops, that was rather messy. Let's try that. Nope. That, there we go. The other thing I looked at was, what if our transformation is to take and add a number on the outside of the function? So earlier I looked at, for example, the sine of x plus 1. That right there is a vertical shift. And that one's pretty straightforward. If A is a positive number greater than 0, then that's a shift up. And if A happened to be a negative number less than 0, that's going to be a shift down. We can double check that in our graph. So I can just delete just y equals f of x, right, which is just a copy of the red function above. Turn it back on. And earlier we looked at a +1, right? That moved it up. A -1 would drop all those points down. I could go further down if I wanted to. And you can combine these also. So we could do a stretch and a shift if we liked. So I could have it drop by 2 there. And then I could also say double the wave. So that's going to give me a taller wave, but dropped it down by 2. Now I want to point out something interesting here. Notice the drop of 2 here. That's the center line of this new function. So if I graph y equals -2 to indicate the drop of 2, you can see that purple line goes right through the middle of that wave, cutting it in half. So basically that -2 up here shifts the function down 2, and it doesn't matter how I stretch it after that. So instead of doing a 2 times out there, I could do a 3 times. It's still going to be centered at y equals 2. That's still going to be the midline, no matter how I do that stretch or compression. Even if I do like 0.5 there, still centered on y equals -2, because that was the shift that I made here. So transformations with respect to y are pretty straightforward. What you see is what you get. Transformations with x are a little trickier. So let's show you what I mean by that. Hopefully this is, you remember this. So for example, if I do a -2 on the outside, that drops it by 2. If I do a +2, that raises it up 2, right? Same shape, just shift it up 2. What if instead I put it with the x inside the parentheses? And you may remember this from your work in math before. So horizontal transformations. So starting with, say, the one we've been playing with, f of x equals the sine of x, what is going to happen if I look at the graph of, switch color here, y equals f of x plus 1, right? So that would be the sine of x plus 1. Now vertically that shifted it up. So will this be a shift to the right because of the plus one? Well, let's graph it and see, and then we'll try to figure out what happened. So I'm just going to put a plus one here. Which way did it go? The green function, that peak here is to the left, not the right. Interesting, it went backwards. Remember, the peak of the original sine function happened at pi over 2. At pi over 2, the sine reaches its maximum value of 1. So what if instead of a plus 1, we do a pi over 2? Graph it. So what happened, instead of going to the right pi over 2, the function shifted to the left. It went backwards. Why? That is because of the essence of what it means to be a function, which I'll get to. Interesting. This ended up being a shift left. So horizontal shift left 1. I also graphed y equals the sine of x plus pi over 2. And that one was a shift left in the negative direction by pi over 2. So what happened there? Well, let's think about the original sine function. So originally, if I consider, say, the number pi over 2, the sine of pi over 2 is equal to 1. Right? This is just a fact. This is what we developed when we were playing around with the basics of what the sine meant. Sine of pi over 2 is 1. End of story, exclamation point. So the only time I'm going to get 1 as the answer if the input is equal to pi over 2. So if the input is equal to pi over 2. So if I look at this function up here, there's my input. I need that input right there to be equal to pi over 2 if I want 1 to be the answer. Well, what number can you plug in for x to get pi over 2 for the answer? So in other words, x plus pi over 2 is equal to pi over 2 when x equals what? Well, x equals 0 is the only way that's going to happen. How did I get that? I'll solve for x. So I know that the only time, well, certain relatives of pi over 2 give me 1 as the output. So I want to know what input here is going to give me 1. Well, that means the input has to be pi over 2. I replace the x with x plus pi over 2. So when is x plus pi over 2 going to be equal to pi over 2? Subtract pi over 2 to solve for x. Pi over 2 minus pi over 2 is 0. So that tells me x has to be 0. So if I plug in 0 here, I will get that peak of 1. And that's what happened on the graph. So on the outside, because of the way we calculate functions, y as a function of x, outside stuff's pretty straightforward because it happens after we do the calculation. But now we're asking questions about what happens before we do the calculation, which means we need to solve an equation. When you solve an equation, you undo addition by doing a subtraction. You undo multiplication by doing a division. Everything's backwards when you solve equations. So it turns out, function-wise, if we do a transformation inside the function notation, that's like solving an equation from the old function, and everything's backwards. So here, notice to get that peak, I had to plug in x equals 0 because the sine of pi over 2 is 1. All right, so it's kind of counterintuitive. Hopefully you remember seeing that in a previous math class. So let's summarize these horizontal transformations. So horizontal transformations, what kinds can we have? So given some original function, y equals f of x, we could do an addition inside. So something like f of x plus a. And one of two things will happen depending on whether A is positive or negative. So this is going to be a horizontal shift. Oops. That shift is going to be to the left when A is less than 0. Oh, sorry, greater than 0. I lied, like we saw a moment ago. So if A is positive, we move in a negative direction. We'll get a horizontal shift to the right when A is less than 0. That is negative. Double check. So if in here I replace the positive with a negative, you can see the green wave moved to the right. So I'm going to demonstrate that with a little trick here. Let's get rid of that. Let's type H equals 1. And then the program's going to make me a little slider here for that. So let's go from negative 2 to 2 and not worry about the step. And then we're going to start at 1. Let's put it over to 0 for a sec. All right. And then, this is kind of cute. I want to graph f of x plus that number h there I'm putting in there. Oops, I guess I need to do a y equals that. And can you please give me a different color? Somewhere here, there's a color picker. Where's the color picker? There. Oh, I've done this before. Come on. Settings. There we go. Let's make you green again. All right, so I have my green function sitting on top of my red function. H is 0, which means I haven't shifted. And if I take and make H a positive number, you should see that that green curve is going to move to the left as H gets more positive. And as H gets negative, it should go the other way. Isn't that cute? All right. So those are backwards what I thought they should be. Now, other thing I can do in there is I can multiply x by something. So that would be a different kind of effect. So instead, what if we look at something like f of a times x? What's going to happen there? Well, it's going to depend on whether a is positive or negative, whether a is a fraction or a is bigger than 1. So let's play around with that. So, for example, what would the sine of 2x look like? Now, usually when you double something, it gets bigger. But remember, when we do things inside the function notation, it's counterintuitive. It goes backwards from what we expect because we're basically solving an equation to figure out what goes on. So let's just turn that off for a sec. We'll come back to you. So what if I do 2x instead? So now what I can see is horizontally, the wave is narrower, right? It's the opposite effect there. That's a horizontal compression. Compression factor is 2. If I put a fraction in there, like 0.5, then I've stretched the wave out, right? So counterintuitive. So when we do transformations inside the function notation, it's backwards of what we expect. Outside is exactly what we expect. Oh, and then we have the other interesting thing about if we do a negative. So what if I multiply by -1? What that does is it flips the wave horizontally around the y-axis. All right, picture that in your head there. It's a horizontal flip, which means about the y-axis. Let's write that down. So A here is going to be a horizontal compression when A is greater than 1. And the sign thing is just a flip. So it turns out the key is really, it's the absolute value of A. So it doesn't matter whether A is 2 or -2, it's still going to be a compression. Let's double check that in the graph. So if we do 2x, we can see we have that narrower wave. And if I did y equals -2x, oops, f of -2x, I'm still going to get that squished wave. So turn this one off for a sec, right? There's that squished wave. There's that squished wave, right? But this negative is a squish and a flip around the y-axis. So if we turn, let's pick a new color for this one so we can see that better. How about purple? Sure. So if we turn off the sign for a second, I can see the green and purple waves. The purple is taking that green wave and rotating it about the y-axis, which is a horizontal rotation. So again, if A is something like 2 or 3 or -2 or 3, it's a compression. We're going to get a horizontal stretch if A is a proper fraction. And so it's going to be a proper fraction if the absolute value of A is less than 1, which means A has to live between 1 and -1. So another way to state that right there. We did that earlier. And then if A is negative, then we get a horizontal flip about the y-axis. So we get a horizontal flip. And that would be about the y-axis anytime A is less than 0. All right, so the point of this is that if we see a transformation of a trig function, if we know what the original trig function is, then we know what the new one looks like. So let's play a game with that. Just a moment.